Okay, so today we're going to talk about slope fields and Euler's method. So this is a mixing problem that could be adapted to represent pollutants in a river, or absorption of medication into the bloodstream, or migration of species in and out of an ecological system. So let's see if we can come up with the initial value problem that needs to be solved to answer this question. So at time t equals 0, we have a tank that contains 4 pounds of salt dissolved in 100 gallons of water. And suppose that the brine containing 2 pounds of salt per gallon, that brine containing 2 pounds of salt per gallon is allowed to enter the tank at a rate of 5 gallons per minute. So you have some brine already in there, 4 pounds in 100 gallons, and you're pouring more brine in that's at a different concentration. 2 pounds per gallon, and it's going in at 5 gallons per minute. And then we're going to assume that it just immediately mixes completely. It's like being stirred constantly or something. As soon as it goes in, it mixes. And then the mixed solution is going to be drained from the tank at the same rate, 5 gallons per minute. So what I want to find is the amount of salt in the tank after 10 minutes, the total amount of salt. So let's let that be some variable Q for quantity. I'm going to say let Q be the total amount of salt in the tank. Okay, but the total amount of the salt in the tank is a changing quantity, right? Because you're pouring some in and you're draining some out. So how much salt is in there depends on time. So this is really a function, Q of t. All right, and what they've told me about Q is about its rate, right? They've told me some stuff about how the amount of salt is changing in there. So that means I'm going to write a differential equation whose solution, hopefully, will be Q, the amount of salt at time t. Okay, so the rate of change, the amount of salt, the rate of change of the amount of salt in the tank, right? dq dt. That's the rate at which the quantity of salt is changing. In general, when you have a rate of, like an inflow and an outflow, your rate of change is the difference, right? You're going to have the rate in, the rate at which salt is coming in, minus the rate at which salt is going out. All right, so how fast is the salt coming in? Yes, 10 pounds per minute. How'd you get that? 2 pounds per gallon, right? So the gallons cancel. So yeah, if you do a quick little dimensional analysis, we want to know the rate at which salt is going in, right? And we measure salt in pounds. And so we're measuring salt, total amount of salt in tank measured in pounds, right? And t is time, which we're measuring in minutes, right? So if I do a little, I say, well, 2 pounds per gallon times 5 gallons per minute, right? Your gallons cancel, and you end up with 10. 2 times 5 is 10 pounds per minute. That's the rate of change that salt is flowing into the tank. How fast salt is going in. So this is 10. All right, and then the rate at which it's going out, I always find this one a little bit trickier, because the rate at which it's going out is how much salt is leaving per minute, and it's a little bit harder because the concentration of the drainage is not constant, right? So like the concentration of the salt water coming in was 2 pounds per gallon, and it's always that. But then that 2 pounds per gallon is mixing with all the brine that's already in there. And when you drain it out, How many pounds per gallon is in that water that's coming out? I don't know. It's not a given in the problem. How would you calculate how many pounds per gallon there are in this big vat of brine? Well, how many pounds of salt are there at any given time t? Nope. It's changing. No, you're not losing it at the same amount because the amount that's coming out is a different concentration than the amount that's going in. Yeah, it says the mixed solution is drained from the tank at 5 gallons per minute. So the question is, we have to know how much salt is in that mixed solution, right? How much salt is in the tank at any given time t? Q. That's what we defined Q to be, right? Q of t is the amount of salt in the tank at time t. So if I need to know the concentration of the water coming out, I need to know how much salt is in there. So the salt is Q. The salt's concentration is Q, right? And I'm going to divide that by how many gallons are in the tank? 100. So this is Q pounds per 100 gallons, right? So that's what we did with the, we had 2 pounds per gallon. Now we don't know how many pounds per gallon, it's Q pounds per gallon. And then you have to multiply that by 5 gallons per minute, the rate at which it's draining out. Gallons cancels. And you end up with 10 minus 1/20th Q. And that is my differential equation dq dt. Okay, so that is how the amount of salt in the tank is changing with time. 10 represents pounds per gallon flow in, sorry, pounds per minute flow in, and negative 1/20th Q, that's your pounds per minute flow out. And then Q of 0 equals 4. Where does that come from in this problem? Well, how do we know Q of 0 equals 4? The very first sentence they gave us, right? At time t equals 0, a tank contains 4 pounds of salt. So the amount of salt, Q, at time 0 is 4 pounds. All right, so I would like to solve this initial value problem. What should I do to do that? Anybody remember a handy technique? Can we separate? Let's try. So if I want to get the Q by itself, I'm going to have to divide both sides. I'll multiply both sides by dt and divide both sides by this whole thing. So I have 1 over 10 minus 1/20th Q dq equals dt. I think this is just going to look a little cleaner if I write 1/20th as 0.05. All right, so now that I've separated it, you know, I've got all my Q's on one side and all my T's on the other. Now I can go like this. So the antiderivative of dt is t plus c. Antiderivative of 1 over 10 minus 0.05 q. How could we do that? Yeah, so you could try to maybe say 10 minus 0.05q to the negative 1. And then it would be negative 2 over negative 1, but then you'd have to compensate for the chain rule somehow. What if that just said 1 over q? What would the antiderivative be? The natural log. Okay, so how could I make it just look like 1 over q? Because that's easy. Yeah, I'm going to do a u substitution. So first thing I'm going to do is I'm going to factor a 0.05 from the denominator so that I don't have any coefficient on q. So 0.05 times what would give me 10? It's too early in the morning. 200 minus q dq. Okay, so I can pull the 1 over 0.05 right out of my integral. And this becomes 1 over 200 minus q dq. This one, you could do a u substitution, or you could do what Matt was just suggesting, sort of like try to compensate for the chain rule without having to formally write down the u substitution. So my antiderivative of 1 over something is the ln of that something. But then if I were to take the derivative of this, the ln of 200 minus q, I would have 1 over 200 minus q times what? Negative 1, derivative of the inside. So if I just put a negative out here, I'll be all set. So there's my antiderivative. So now what do I have to do? Am I done? The question was how much salt is there after 10 minutes? Does this answer the question? No. I need a function q. I need to solve for q. All right, so I'm going to multiply both sides by negative 0.05. Why didn't I multiply the c by negative 0.05? It's a constant, yep. Why does that mean I don't have to multiply by negative 0.05? Well, I did. I just said it's still an arbitrary constant. Yeah. All right, so now if you have an equation of the ln of some stuff, how do you get that stuff out of the ln? Raise e to both sides, yeah. So e. Because e to the ln of some stuff gives you the stuff back. And then this is e to the 0.05t negative times e to the c. And e to the c is just another arbitrary constant. So I'll put c e to the negative 0.05t. And then to solve for q, I just have to subtract 200 and multiply both sides by negative 1. So I'm going to have q equals and I suppose I should put a negative there, but c, I guess, is an arbitrary constant, which could be positive or negative. It takes on all values. So if I put a negative there, it doesn't really matter. Oh, yeah, because I subtracted 200 and then I have to multiply by negative 1. Yeah. And then to figure out what c is, if you put a negative in front of c, you'd get the same answer when you plug in your initial value. Yeah, yeah. So if right? But negative c, because c is an arbitrary constant, if you put a that means that it takes on every value, right? It just could be any value, negative infinity to positive infinity. So the negative sign doesn't really matter, right? So, but I could leave it there, and I'll still get the same answer when I plug in my initial condition. So I'm going to plug in 0 for t, and that means I have negative c e to the 0 plus 200. That has to equal 4. Okay, so I subtract 200, and I have negative c, because e to the 0 is 1, equals 4 minus 200 is negative 196, which means that c is 196. So just have to put the c back into my function q. Negative 196 e to the negative 0.05 t plus 200. So that's my function that models the amount of salt at time t. How do I answer the question now? Remember, the question was, how much salt is there after 10 minutes? Yeah, how do I get a numerical answer? Plug 10 in for t. Q of 10. £81.1. All right, so that's kind of a lot of work, right, to set up and solve this differential equation. We're now going to draw something called a direction field or a slope field. And this involves drawing a little tangent line of the appropriate slope at a bunch of different points. Okay? Because I have a differential equation that says dq dt equals 10 minus 1/20th q. Right? But dq dt graphically represents the slope of a tangent line. Right? That's what a derivative is, the slope of a tangent line. So I could take, in the qt plane, time, quantity of salt. At any point in this plane, I could calculate the slope of the tangent line. Right? So what I'm going to do is, at a bunch of points, I'm going to calculate the slope of the tangent line and draw a little tiny tangent line. And then that will sort of tell me the direction that q takes. So let's see, at 0, 100, if I plug in a 0 for t and a 100 for q in my dq dt formula, I would have 10 minus 1/20th of 100, which is 10 minus 5, which is 5. dq dt is 5. And if I plug in 50, 100, I still get 5 because there are no t's in my equation for dq dt. So the only thing that matters is q. So anytime q is 100, I have 5 for dq dt. All right, what if q is 150? What's 1/20th of 150? 7.5. So this is 10 minus 7.5, which is 2.5. And 1/20th of 200 is 10. 10 minus 10 is 0. And 1/20th of 250 is 12.5. And if you do 10 minus 12.5, so I get negative 2.5. 300 divided by 20 is 15. 10 minus 15 is negative 5. So I know what the slope of the tangent line is of this mysterious function, right? I solved for it on the previous page, but If I didn't know what it was, I could say, well, I don't know what it is, but I know the slope of its tangent line in lots of different places. So I'm going to sketch a few different slopes, all the slopes that I found. I found that whenever Q is 100, which is right here, all along this line, my slope is 5, which is a pretty steep tangent line. So I put a little steep tangent line. Doesn't matter what t is. When Q is 100, slope is 5. All right, and then when Q is 150, so if I go up a little bit, my tangent line gets a little less steep. It's only 2.5. So now maybe it's like this. And at 200, my slope is 0. That's a horizontal tangent line. And at 250, my slope is negative 2.5. So now it's negative. Same steepness as this guy, but switched direction. And then negative 5 at 300, so really steep. All right, so this thing is called the slope field. Okay. On the slope field, we can sketch solutions. Like this is telling us what all the solutions look like. So it looks like no matter where you start, if you start below 200, the amount of salt, because this is time and amount of salt, the amount of salt looks like it approaches 200 with any initial condition. So we can sketch a few different solutions just by following the slope field, right? You might imagine that these are like lines in a parking lot, and the solutions are like cars that have to try to follow the directions of the lines. So if you start at time 0, you have 100 pounds of salt. It's going to increase towards 200. If at time 0 you have 300 pounds of salt, it's going to decrease down to 200. So several solutions. You can sketch them. And those look exponential, right? They sort of are exponential, shifted so that they approach 200 instead of 0 like most exponentials do. So this graph validates the long-term behavior of the salt we predicted, because our equation, right, for Q of t was negative 196 e to the negative 0.05 t plus 200. So if I take the limit as t goes to infinity of that thing, what is that limit? What happens to e to a negative exponent? Yeah, this whole term is going to approach 0. That whole term goes to 0. So my limit is 200. And my slope field bears that out, right? It looks like no matter where you start, you approach 200 pounds of salt. So what do you think the equilibrium solution is in this problem? $200, yes, that's the balance point. If you start with 200, if you start with exactly 200 pounds of salt, you'll just stay there forever. So that's called an equilibrium solution. Actually, I should say Q equals 200 is my equilibrium solution. All right, so slope fields, drawing slope fields by hand is sometimes not that helpful because you really have to be precise about the actual slope. So having a computer draw slope fields for you is really handy, because then you can get more, you can do more points, it's less tedious, and it's more accurate. So here I have a couple of slope fields. I want to sketch the solution to the differential equation that has this slope field and that passes through the point indicated. So all you have to do is kind of follow the arrows, right? This looks like it's going to go like that. And then I have to kind of go backwards in time also. Looks like it came from over here. And then for this one, just kind of follow the arrows. Looks like that. And if I go backwards in time, looks like it came from over there. All right, I want you to try one. I just sketched the slope field on these 12 points that I drew here. Sketch a little slope where this is your differential equation. Y prime, that's your dy dx, or your slope of your tangent line, at each of those given points. So you have an xy, plug them in, get the slope, draw it. Okay, so I made a little table here where I put in the point and then another entry for the slope of the tangent line, which is just y prime, right? So you plug the point into your equation for the derivative, x squared plus y squared minus 1. So 0 squared plus 1 squared minus 1 is 0. 0 squared plus 2 squared is 4, minus 1 is 3. 0 squared plus 3 squared, that's 9, minus 1 is 8. And 0 squared plus 4 squared is 16, minus 1 is 15. And 0 squared plus 0 squared minus 1 is negative 1. 1 squared plus 0 squared minus 1 is 0. 2 squared, that's 4, minus 1 is 3. I'm going to get 8, 15 again. And then negative 1 squared is positive 1, minus 1 is 0. That's going to be 4, minus 1 is 3, 8, 15. So then I just plot these as little tiny tangent lines, little tiny lines with these slopes on the points indicated. So at 0, 1, my slope is 0, so it's a little horizontal line. At 0, 2, oh, I plotted more than I did the wrong points. Oh well, okay. So do I have 1, 1? I don't have 1, 1 done. Okay, when I plug a 1 and a 1 in, 1 squared plus 1 squared is 2, minus 1 is 1. So my slope here is 1. And if I plug in 2, 1, 2 squared is 4 plus 1 squared, that's 5, minus 1 is 4. So that's steeper. And if I plug in 3, 1, I get 9 plus 1 is 10, minus 1 is 9. So really steep. Okay, so 0, 0, I have that one. That was a negative 1. And 1, 0, I have that one. It's 0. 2, 0 is 3. 3, 0 is 8. Pretty steep. So you can see that doing this by hand is hard because it's hard to differentiate between a slope of 8 and a slope of 9 when you're just drawing a little tiny line. But you get the idea. Let's skip this, and we'll come back. It's one of the challenges, but it's kind of a fun one. So we'll come back later. Make sure we get through everything else. Okay, so let's confirm some of the data in this in the following graphic for the slope field of dy dx equals y minus x. Okay, so here I have x's going along vertically and the y's going along horizontally, and I've kind of put the slope at each xy point in this table, and then plotted them from -3 to 3 and -3 to 3 here. Do you see any equilibrium solutions? Any place where y just never changes, horizontal slopes? Oh, okay, so at 1, 1, you have a horizontal slope, yeah, but an equilibrium solution means that if you're here, then you stay flat forever. Equilibrium means a constant solution, but this is not constant because it, it'll drop down like that if it follows the arrows. So no equilibrium solutions. An equilibrium solution, like I said, this 200 was an equilibrium solution because if you start at 200, you always stay at 200. That's a constant function, y equals 200. We don't have anything like that in this slope field where you just have a row of horizontal tangent lines. Okay, so on the graph at the far right, I had a computer draw in more than just the integer slopes, right? So this little table calculates the slopes at integer points. But that's the great thing about a computer is you can tell it to put a little slope every 2/10 of a point, right, instead of just integers. And you get a better picture. So I want to plot the points -3, -1, -3, -1, -3, -2, 0, 0, and sketch the solutions to the differential equations that pass through those points. So if I start at -3, -1 and try to follow these arrows, it looks like they just go up, something like that. But if I start at -3, -2, it looks like I just follow this straight forever. And if I start at 0, 0, it's like it goes like that. So the behavior of your solution can be very different depending on your initial condition. So our goal is, this is very qualitative, right? You just kind of draw pictures and you just try to follow the arrows, and you can't answer a question precisely using this kind of method. This is like, oh, if I start at 0, 0, like you can tell what's going to happen as you tend towards infinity. Like as time goes on, this is going to get smaller and smaller and smaller. But if you wanted to give it a number, like how small is it when t equals 10, this is not a good approach for that. So our next goal is to come up with a way to approximate the solution to initial value problem, where you have y prime equals some formula, and you're given an initial value. So here's how it works. You start at an initial value. Calculate the slope at that point using the differential equation. Okay, the slope tells us what direction the solution is going to head in. So you head off a small distance in that direction. You take one small step in the direction that your differential equation indicates, and then you stop and you're at a new point. Recalculate the slope from the differential equation at that point, and it'll give you a new direction, right? It's kind of like a scavenger hunt, right? Each time you land someplace new, you get a new clue. You land at a new point, and it gives you a new direction to head in. Okay, so this distance, this technique that we're developing is called Euler's Method. So here it is translated from English, which is what I just sort of gave you there, to math. So Euler's Method says, first you have to choose a step size. That's our small direction. Like each time we get a direction, we have to move in that direction a small step. So we choose a delta x to be our step size. And then we compute x1, right? So we take our x0, which is where we initially started, and we add delta x to it. That's going to be our next small step in the x direction. And then to figure out the y value that corresponds to that new x value, you take your old y value and you add delta x times f of x naught y naught. And the reason that is, right, is because delta x times f of x naught y naught, that's y prime, or dy dx, right? This is a very small change in x. The smaller the step size, the better this approximation, right? So we go like that. And this just leaves you with dy, or a change in y, right? So you start at your old y, add a small change in y, and you end at your new y. So you keep doing this, keep getting a new point, get the slope, and then move in this direction a small distance. All right, so we'll do one. I think you'll see how it works when we do an example. So we're going to use a step size of 0.1, that's my delta x. And I want to approximate the solution to y prime equals y minus x with an initial value y of 0 equals 2. And I want to know the solution at x equals 1, right? So I want to know y of 1 equals what? Okay, so I know about y's derivative. I want to know the value of y at 1. Well, I know the value of y at 0, right? The value of y at 0 is 2. So let's make a little table here where I'm going to have xi, yi, f of xi, yi. And we'll start with that. So my initial point, my initial xy is 0, 2. Okay. And then I can plug 0, 2 into my differential equation to get a slope. Right? If I plug in 2 for y and 0 for x, my slope comes out as 2. So then I have a delta x. And then I have a new xi. I need to calculate delta y, my change in y, which is delta x times f of xi yi. And then I have to add that to my old y. Okay. So delta x is always going to be 0.1. That was a given. So my new x is my old x plus my delta x, 0.1. My delta y is my delta x times my slope. So I do my 0.1 times 2, which gives me 0.2. And then you add your old y of 2 to your delta y of 0.2, and you get 2.2. So now I have a new xi, yi, 0.1, 2.2. And then you have to do the whole thing again. And we have to keep doing this until we get an xi of 1, because I want to know the y value when x is 1. Okay, so let's, if I plug 0.1, 2.2 into the differential equation, y minus x, I would do 2.2 minus 0.1, which is 2.1. It's my slope at that point. Delta x is always 0.1. My new xi is my old xi plus my delta x, so I have 0.2. My change in y is delta x times the slope. 2.1 times 0.1 is 0.21. And then my new y, I should call this new y. My new y is my old y plus the change in y. So 2.2 plus 0.21 is 2.31. So then I come back around and I say my new point now is 0.2, 2.31. This is going to take a long time. Okay, so I plug those 2 points into the differential equation to get the slope. And I would say 2.31 minus 0.2 is 2.11. delta x, always 0.1. My new xi is my old x plus my delta x, so 0.3. My delta y is delta x times the slope. 2.11 times 0.1 is 0.211. New y is old y plus delta y. So 2.31 plus 0.211 is 2.521. Did I do that right? Yeah. 2.3. So that's 0.5, 2. Yeah, that's right. Okay, so then you come back and put in your new x and your new y at the start of the table. So I have 0.3 and 2.521. Plug them into your differential equation. 2.521 minus 0.3 is 2.221. Delta x is always 0.1. My new x is my old x plus delta x, so I have 0.4. My delta y is f of xy times delta x, which is 0.2221. And then to get my new y, add your old y to your delta y. So 2.521 plus 0.2221. That's going to be 2.7431. Yeah. Okay, you finish. Go till you get to x equals 1. Oh, why didn't you tell me when I did that? That's supposed to be 2.41, so that all the rest of it is wrong. So that's okay. You guys have to finish it anyway. Okay, so just keep doing this till you get x equals 1. Okay, so I finished writing it all out, and we end up with when x is 1, our y value is about 4.59. And a key to doing this is that you can't round during the method, otherwise the rounding errors compound, and you end up like way far off from this number. So that's why I have all these decimal places written out here. And sometimes I didn't write them all, but they were all in my calculator, right? So I used the actual whole thing in the calculator. So that means that I was able to, without finding an equation for y, all I had was this differential equation is y minus x, and that y of 0 equaled 2, right? This is a non-separable differential equation. I can't solve it with the techniques that I know right now. So even though I can't get a formula y of x equals, right? I can't get a formula. I do know that y of 1 is approximately 2, right? I can use information about the slope to take little tiny steps until I get to 1, x equals 1, and I can know that the, I'm sorry, it's not about 2, it's about 4.59. Till I get an approximation for the y value at 1. So that's Euler's method. So since we don't have analytic tools to solve that differential equation, you'll have to wait until Math 204 to see how to get an exact solution. That said, I've already taken Math 204, so I can tell you that the exact solution of that differential equation is y equals x plus 1 plus e to the x. So let's confirm. It also satisfies the initial value let's confirm that it satisfies the differential equation and the initial value. Okay, so y prime, if y equals x plus 1 plus e to the x, then y prime equals the derivative of x is 1, the derivative of 1 is 0, and the derivative of e to the x is e to the x, right? So that's my y prime. And then y minus x, well, y is x plus 1, right? Plus e to the x, that's my y. Subtract x, and you just are left with 1 plus e to the x, which is the same thing as y prime. Okay, so I showed that for this equation, y prime is the same thing as y minus x. So that is confirmed. They both equal 1 plus e to the x. And then let's just double check y of 0. That would be 0 plus 1 plus e to the 0, and that does equal 2. Okay, so this guy is a solution to the differential equation, and it satisfies the initial condition. So if I use that function to check my accuracy, I just have to plug a 1 in there, and I get 1 plus e to the 1. So 1 plus e, well, that's 2.718, so that's 4.718 approximately. And our approximation was 4.59, which is not too bad. So Euler's method definitely has some error in it, but it is a good way to get approximations. And the smaller your step size, the better your approximation. If I needed a better approximation than this, I could have used a step size of 0.01, taken 100 steps to get there. Okay, so, there's only 5 minutes left. In your last 5 minutes, you can look at project 5, look at the quiz, but know that you can't talk to each other about it. Finish up test corrections if you haven't yet. Those are due 1 o'clock this afternoon, no exceptions.